Okay, well, hi everyone. In this video, I'm going to show you how to predict the permeability in uncored wells and intervals. Well, actually, this is a big question because, as you know, permeability is a very um, interest and important property, and it should be uh, estimated carefully or predicted very carefully. And as you know, there are a variety of ways, different ways and approaches that have been demonstrated um, from scientists before. So in this video, I'm going to show you how to predict the permeability using two methods. I'm going to demonstrate the classical one and the flow zone indicator as Kozney Carmen, the original, actually, not the modified, the original equation and the original method of predicting the permeability. Um, uh, Basically, as you know, the porosity is the ability of a rock to storage the fluid, while the permeability, the ability of rock to transmit the fluid. What is the difference between the permeability and the porosity here? So the porosity or permeability, maybe we can say it's more complicated more than the porosity. Well, this is from this point, the first one, classical. It's assume there is a direct relationship between the permeability and the porosity. While in fact it's considered one of the demerits or disadvantages of the classical one, but it is at the same time useful if you can, in a fast way, you can estimate the permeability. Well, as you know that the permeability is grain size dependent, where the and flow units should be taken into consideration. Where in the classical one, as I said, it's assumed that there is a direct relationship between the permeability and the porosity without depending on the grain size and other things, important things which should be taken carefully into consideration carefully. So this is a classical method, while as I said, the Kozney or the Kozney Carmen equation, which is the flow zone indicator, and it's used by finding the flow zone indicator after finding the reservoir quality index flow and normalize the effective porosity from these two laws. Okay, and then from the flow zone indicator I can separate different permeability, porosity intervals depending on the flow zone indicator. So the classical one, if I assume that we have 3 units for a definite reservoir, and the classical method application, if I want to estimate the permeability of the Uncored, as I said, the Uncored wells and intervals. As you know, we have the porosity that have been estimated from the well load. So I have the porosity for different intervals. Okay, for each 1 meter, for example, or 1/4 meter, or less and or more, depends on your interpretation. So in front of a definite depth, there must be a permeability, and that is not gonna happen because we know that the core is extracted from a definite interval, and it is very let's say not the thickness and the length of the core is not on in the entire of the well. So of course we have uncored intervals, and even we have of course different wells. I'm not extracting for each well a core, so we have very limited numbers of cores and limited intervals. So in this way, for a definite layer or for a definite unit, let's say for a unit MA, I'm going to find an equation in the classical method that linked between the porosity and the permeability from different wells. For example, I have 4 core wells, so I have to separate the unit for that different for those different wells, and the unit of MA, let's say, separate the numbers or the values of the permeability and the porosity for that unit, and then make a plot between the permeability and the porosity and find the equation. So if we drill in the future a new well in a definite location, I can use this equation to find the permeability depending on the core values for that for the cores at the beginning, the cores values of that unit. And the way is like this. So we have the phi and we have the permeability for a definite, as I said, for a definite unit. We have MA here, MB1 and MB2. So we can make a plot for between the permeability and the porosity here. And the x-axis is the porosity, and the y-axis here is of course it's a logarithmic. It is logarithmic. So come to modify and make it more clear. And as I said, this is in the logarithmic scale, and it will intersect with 0.11. Okay, and I can add a trend line here and find the equation. Okay, and find the equation. So we have the equation is 0.0064 exponential for the power something multiplied by the x, which is the porosity. We have y, the permeability, x in the porosity. So by the way, the R squared is the correlation coefficient which reflect the strong relation between the y and x. We have a good relationship between the property, these two properties, the porosity and permeability, for that unit, which is the MA. So now I can use the porosity for that well or for different wells, the porosity of the log porosity, and it is going to substitute with the x, okay, each value of log porosity with the x, so I can easily find the permeability for that unit. In the same way, I'm going to find the permeability equation for, let's say, unit MBO, for the unit MBO. And so on. If I for example, I take only 3 units here. If you have different units, more than 3 or 4 units, you can find equation for each one and then apply the porosity logs to find the permeability in the uncored intervals and parts. Okay, so this is the way it's like this. This is in the log of cosmic scale. Intersect with 0.1, and we can add a trend line, exponential, and find the correlation coefficient. The correlation coefficient. Okay. So this is for unit for the unit MB1, and we can of course for example, let's say as I said, you can find the equations for the other units, so you can easily find the permeability of the other units. Axis title, for example, not the axis, I want the main one, which is the x-axis. Just a minute, please. We have chart title. This is for MB1. Okay, this is for the MB1, and this is for the MB, or for the M, or the MA. Okay. So we have good correlation coefficient. Now here the correlation coefficient is somewhat bad. Well, as it's approached to 1, it's better. Okay. Reflect the good correlation coefficient between the Y and X. So this is in general how can we find the permeability using the classical method. So the next one is the next method is, which I'm going to clarify, is the permeability prediction by using the flow zone indicator. And for example, of course, the same way if you can apply the flow zone indicator for your entire data, which is the same the previous data, of course, but I haven't separate the values of the porosity and the permeability depending on the zones depths, but now it's optional to you. It's better to be more precise if you can find equations of each flow zone indicator for the same unit. For the same unit, or you can find flow zone indicator equations for the whole core data, without separating the units, Okay. Of course, they have different units in the properties, because this is the basics why we have make intersections between the units, because we have the different in properties. So it's more precise if we find different flow zone indicator units equations for each unit. So now, for example, we have let's clarify the general idea of the flow zone indicator. Of course, I said previously that the permeability of strong dependent on the grain size, and the Kozney Carmen method take into consideration the flow units here. So it's more effective than the classical one. Okay. So depending on the literature of course we have three equations to find the flow zone indicator, starting from finding reservoir quality index or phi z. Okay, and we have a flow zone indicator here. So reservoir quality index equal to 0.0314 by let's begin from the cell. Okay, by the permeability over the porosity for the power 0.5. Okay, again for the other cell we have the permeability over the porosity for the power 0.5 for the power 0.5. Okay, easily we can find the reservoir quality index for the other cells depending on what we have done the first two cells. And it is the normalization of the porosity. So it is the porosity over 1 minus porosity. Okay, again to be sure that everything is okay, over 1 minus 5, and then find the flow zone indicator for the rest of the data. Now the FZI is the reservoir quality index over the phi z, and it's E over Fn. Okay, E over Fn. Okay, let me see. So now I want to find the flow zone indicator of only number without digits. So I'm gonna to round the flow zone indicator. Okay. Round. Sorry. Round. Okay, then 0. So each digit, the first one is going to be nearly either normalized to 0 or it's going to add a 1 to the corrector. Okay, so it goes, of course, 1 point is going to be 2. In the same way, this one and 0. Okay, so 0.65 is going to be add a 1 to 0 correct, so it's going to be 1. Okay, the same way you can find the flow zone indicator rounded for the rest of your data. Now it's easily can be seen from the flow zone indicator rounded that we have only 2101 without digits. So without digits, so it can be easily filtered. It can be easily filtered. So this is an important point here. Can be easily filtered. Sorry. So now I can filter my flow zone indicator here depending on by using filter panel or tab in the data. So if you can know that we have FZI1 flow unit 1, 2, 3, 0, 5, 6, 7, 8, 6, 7, 9, 6, 7, 9. But high number of 0 a lot, you can notice, and 2 and 3, but the rest, which is 4, 6, 7 and 9 are very little. So I'm going to add the other numbers from 4 to 9 and consider them not going to consider them as a flow unit for each one of them. So I'm going to add them to the 3. So we are going to have only 4 units. Of course, if you have a lot of values of 4, so you have to add another FZI. That means that we have a bigger 4th rod, and that means, sorry, a big flow unit. That means that the permeability here is very high. So in general, if the FZI increased from 0 towards 1, 3, 4 and on, so that means the permeability here and the fluid can be transmitted easily, and the permeability is good. Okay, so I'm going to separate, for example, the flow zone indicator 1, or sorry, at the beginning 0. So you can see it has been hidden all the values of the porosity, permeability, RQI, FZI, and phi Z, and around it of 1, 0, of 1, 2, 3, and on of the FZI rounded. So we have only the FZI rounded of 0 appear on the screen. Now it's easily can make a plot between the porosity and the permeability. So our focus and our goal is to find an equation that link between the porosity and the permeability. So we have the FZI in the FZI method. I'm going to find, as I said, 4 equations beginning from 4 depending on the FZI. So we have FZI equation of 0, 1, 2, 3, because I consider the rest of the numbers as they are very little within the flow unit 3. Okay, right click, select data, and add. You can name this as FZI 0 as you want. So the x-axis here, of course, is the porosity. Okay, and the y-axis is the permeability, and it is of course semi-log. So the log is logarithmic in distribution, of course. The x-axis, and this is logarithmic with 0.1. Okay, can a trend line here, power, and okay, then find the correlation coefficient and the equation, the important one, equation. Okay, well, the correlation coefficient is about 85% here, so it's somewhat good. And the same thing I have to do now is for the rest of the FZI's numbers. So for the 1, only select 1, and you can see this is the equation of FZI. For 2, this is the equation of FZI 2. Okay. Okay, just which we can find. Can see if you make plots between separate. This is the x-axis. This is for the y-axis. Okay, and this is in logarithmic scale. And the trend line of power. And we can find the equation. Okay, and obstacle and the obstacle. Okay. So the obstacle is very high. You can see something error has happened before. So this is the for which one? This is for the FZI 3. So I'm going to add 4, 3, 4, 6, 7, 9 with them, and it becomes like this. So this is the final equation. Now, the same way, you can find the equations of the 2, 1. Only select the values of the permeability of 2, 3, let's say 2 here. Okay, and we have the values of the permeability of 2. So we have to take these the other unit into consideration. And the same way is for the FZI unit. Okay. Now this is in general. Now I didn't separate the equations. Sorry, didn't separate the units depending on the the units. So we can, of course, doing the same thing for the same work for different units. Okay, for the same units for each unit. Sorry, for each unit. So now here I separate the MB2 unit and find the equations around FZI. And we have more than FZI. Maybe the most of them is 0, which just reflect not very good in permeability. And we have the FZI 1 here for FZI for the MB1. And you can see that there are 3, 2, a lot of it's better than the MB2. So if we want to make make a comparison between these two methods for the same unit, so we have done 2 methods here. The first one is the classical, and here the FZI method. And if you want to make comparison, so depending on the correlation coefficient, so we have the classical unit for the MA and the MB1, the R squared is 0.63, and if we want to find the R squared for the MB1 for different FZI, and you can see the difference. So this is for the MB1. Okay, now if you want to make a plot between the porosity and the permeability, we can, okay, as I said, the x-axis is the porosity and the y is the permeability. Okay, so this is for the MB1 FZI 0. For the MB1 FZI 0, this is in log cos and okay, and this is in the inverse. Finding a trend line at power for the exponential for the classical or the classical. So it's about 85.6%. Okay, this is the R squared for the MB1 FZI 0. Now we have the classical unit MB1 0.6. Okay, memorize this number, 0.6 something. For the one, it is also, we have to, of course, 0.86 something, and for the same can find the equations or the other. For example, let's say for 2 FZI 2, here we have FZI, sorry, I didn't filter around FZI. Only for the 2 we have only this is deselect the number. Okay, now select the y-axis, sorry, the x-axis is the y, and the y-axis here. There is permeability. Okay, so this is for the FZI2. This is for the FZI2. Logarithmic. We have the inverse and add a trend line, which is 4, and find the R squared, which is look to the R squared here, which is 0.98. So for different FZIs, we have R squared is high. Okay, for the same unit, and we have the R squared is 0.6. You can find the course the R squared for the other FZIs, for 2, for 3, also the same thing you can done. Okay. We can select data and edit, of course. These are our data. So it is the same thing. It's good, good relations. So of course, you can notice that we have good values of the R squared for different flow units. Okay, so in this way we can conclude that the flow zone indicator is better than the classical method, whereas it is take into consideration different parameter, different effective other effective properties on the permeability of the flow unit, the flow grain size, dependent of the permeability, while the porosity is not a grain size dependent, and it assumes that there is a direct relationship between the porosity and permeability. Okay, this is all that I want to show you in this video. I hope it has been interesting and useful for all the interested colleagues and students. So thank you very much. I'm going to show other videos in the near future. So thank you very much and see you soon.